Welcome back to another meetup. Today on Saturday, November 2nd at 1 p.m. Today we have Terry Bollinger, um, just talking about a quick chat on the Nobel Prize, the history of the first cargo called Nobel Prize, and how it deceived generations of researchers and put software at risk, and what are the next steps. Um, Quick background, Terry, he did his Bachelor of Science and his Master's in Computer Science at the Missouri University of Science and Technology. Worked with the government for many years to approve using open source software in federal systems. Um, yeah, his work for U.S. federal agencies has included hard science technology assessments in physics, chemistry, biology, biochemistry, and information sciences. Um, he has helped guide and get funding for artificial intelligence research. Um, and yeah, many years at the Mitre Corporation. And without further ado, Terry Bollinger.
Good afternoon, everybody. And I'm going to try to make the presentation is slotted to up to 3 hours, but frankly, I think short presentations tend to carry the message better. So I'm not going to try to make a long presentation or finish within an hour. I'll be quite happy with that. If there's conversations, questions, we can go on as long as needed, but I will try in the direction of brevity as opposed to just trying to stretch it out. So this particular presentation started when I was very shocked to see that the Nobel Prize in Physics had been awarded to a topic that's not normally considered to be physics. And I think many people in information technology thought that was really cool, but I have a very mixed background where I have a lot of IT background, but also a lot of physics background. And I found that very unusual. The Physics Nobel Committee usually is quite strict about what they decide is going to be a physics topic. And there have been topics, superstring theory being an example, that have gone on for decades that they've just refused to touch it because it didn't meet the criteria for precise physics, testable physics, number of other criteria that they would apply. So I was quite shocked. I was a little bit surprised also that Jan LeCun, I remember thinking that Jan LeCun could easily have been a candidate for that also. And Jan LeCun is someone I know personally. So it was an interesting combination of who that prize was awarded to. So that was my first reaction when I saw that. And then I started digging into it a lot more closely about why exactly did they give this? What was the announcement? What did they say they were giving it for? And that became a far more interesting story, much more interesting story, because one of the two candidates, Hopfield, is very much a physicist. It's just that the particular paper they awarded the prize for was not a classic physics paper, but he had done papers years before, just beautiful work in quantum mechanics, biological molecules, great stuff, and very much in the physics domain. One of my comments on that is Hopfield certainly could have won a Nobel Prize for the physics that he had done. He didn't get one, but it's a very competitive area. But if you look at some of those papers, it's just marvelous stuff where he has insights that brings out the complexity of molecular physics in ways that people have not really perceived. So, the flip side of this Nobel Prize awarding is that even if you don't, as I do not, agree with the specific reason for why it was allocated, you certainly have some very good work. And Hinton, of course, it was one of the three recipients of the Turing Award. Absolutely deserved. Amazing work that Hinton has done. I mean, so much of the foundational work was done by Hinton. And he's part of that trio, of which he's the only one that I've never met or interacted with in that trio. But deserving people, but still an odd combination. Now, given that background, what surprised me most was that, to be blunt about it, the physics for which this was supposedly granted as a Nobel Prize was in fact non-existent physics. So that's not good. and, and with the current timing of what's going on with the world right now, it's especially not good because however you look at it, the Nobel Prize Committee is part of society. They understand what's going on. They've watched this enormous expansion of the LLMs, of the new definition of what AI, which changes every 10 years, as folks who've been in this field know. But the current incarnation of AI is these large language models and the gigantic server farms. And certainly that had some kind of influence on the giving of this Nobel Prize. Either it was considered this is a proven success because all these things are out there, or it was just something that somebody, they got it, whatever it was, they got enthused about this particular topic. And by giving the Nobel Prize, they also give an imprimatur of success for that same undertaking. Well, if you're one of the people who've been tracking this closely, there are a lot of scary things going on with the massive deployment of the LLMs. And that's where you start getting into an interesting interaction between these two. So let's pop in the first one. Simple question, and I would be astonished if your answer was not yes. This is something that happened to me in real life just a few weeks ago. I asked my phone, said, "Are the schools open today?" October 4th, I think I gave the date, October 14th, 2024. And the AI, now I used to get perfectly reliable answers to that kind of question for years. I've gotten good answers to that kind of question. And yet, this time, my answer was no, there were no classes on October 3rd, 2023. So, anyone who has used an AI and used it for a topic with which they are familiar, and maybe there's some exceptions, I have not seen a single case in which when somebody said, "Oh, the answers were so much better than what I could have given." Have any of you encountered that? I'm guessing probably not. What you instead get is always the same thing. It says, well, if you were an amateur, or if you were learning, or if you were tolerant of the errors, yeah, this might be a good mediocre answer. I remember Terrence Tao gave an answer. Somebody was asking Terrence Tao about, what did you think about the math? And that was exactly the kind of answer he gave. Well, yeah, it's not leading edge. And the thing you never, ever see is someone saying, oh, that system was so much smarter than I was, if it's an area that they know. Now, if it's an area that they don't know, it looks impressive. You go like, wow, yeah, this has got lots of good stuff in here. So much information because it has access to literally everything ever written about it. So you get this huge deluge of information, and it's very impressive. But if you poke at the edges and say, yeah, but it is actually better on any point, you always get the same answer. You say, no, it's not. In fact, actually, it's terrible. It can't even get the year right. And it used to get the year right. Now it doesn't get the year right. So why is that? What's going on with that? Why does this happen so much? Now, I like to start out with kind of the conclusion. And the simple answer is right in the name of the model. It is a large language model. What does that mean? It means that for every word you say, there's a probability that another word will follow next. I remember writing a piece of software that did this on a Xenix Unix machine back in, oh gosh, I don't know, in the 80s. And I remember thinking how cool it was that I could get it to respond with a little bit of word mimicry, so it would follow that path. And I remember thinking it made it feel smart. Martin Gardner discussed this in Scientific American. He was fascinated by this idea that if you simply track what word is most likely to occur next and generate that, it sounds impressive. Martin Gardner totally gave up on it when he had a larger system and found out all it does was chunking pieces of information in larger pieces. Suddenly, the intelligent part evaporated. That was back in 70s, 80s, I think maybe late 70s. So it's not like these systems haven't been around. It's not like this concept hasn't been around. It's been around for decades. But what's changed is we have hardware, gigantic hardware that can do it so much better than anything else. But the bottom line is it's still just tracking probabilities, nothing more. And there's a problem with that because probabilities are averages of what has happened. They're not predictive. They're not saying, I understand this. These systems literally are entirely mindless. There's nothing back there to say, well, I should say this. There's no, not even a goal incentive other than saying like, if I say this, I'll get, put it this way. If I say this, I'll get away with it is the blunt way of putting it. And they do. They say, well, if I say October 3rd, 2023, I think I can get away with that. Of course, it's not even thinking that much, but, and of course, it doesn't get away with it, not if you understand exactly what's going on. But because it's trying to do it that way, I see a degeneration, not an enhancement, a degeneration of the answers I get. Because the previous software would have looked for a database, found the exact answer. There would have been everything specific about it. So you still get this situation of just strange answers, and yet they're being pushed at vast levels. And I live in Ashburn. I can tell you why it's being pushed at vast levels. When you invest trillions of dollars in gigantic server farms, all because you think it's going to give better results than anyone ever got before, you are going to be really into marketing that. And I remember even 2 years ago when it first started, I said, this is going to be a ride. This is going to be something because I don't have to go somewhere to see the server farms. I already saw that. I said, if somebody has invested that much money, this is going to be a big push for putting this stuff out there. And that can get into an interesting situation. So what do these LLMs actually do? The way I would describe it, and I think it's not that hard to see that there's a transition there, is that they're really just clever ways of formatting and compressing a lot of data. But people don't express it that way. But that's the whole thing this talk about. If there's anything to get out of this, if you drop out right now and didn't hear anything else, that's the theme I'm really trying to get over, is all of these systems wind up putting data into stored bits. And yes, there's some incredibly complicated algorithms that go into it. They take an enormous amount of energy to do it. But if you think of these as being an active dynamic system in the sense of human brain right now, I have all sorts of state information and a kind of complex interplay of goals. That's not there. None of that's there. This is bits. And the whole thing boils down to bits. And I'll be getting into great detail on that because that's where it really gets fascinating. There's and also some interesting potential. I think some very interesting research potential to help improve some of these issues. So the question is specifically on this work, why did the Swedish Academy of Sciences in 2024 decide to award a prize that no matter how they phrased it in the announcement, they were very careful in how they phrased it. They emphasized uses in physics, and that's absolutely true. So great use of these systems in physics for tracking data, recording data, but those are limited niche uses in which you have full control of the data going in. That's where they're really powerful. So, but they awarded it at a time where what's going on globally is over deployment of what is bluntly a mindless and definitely error-prone data compression algorithm. You put in 100 different versions of somebody's answers, it comes out with an average, says here's some of the deviations from the average, and that's how I'll answer because I only follow words, as if it could think. It can't even think that much. So you get this question, why did you do that? Because these systems are not ready for prime time, no matter how much they've been deployed yet. If you want to put them into a particularly scary use, which is really where the title of this talk comes from, it's when you start doing all of your software with these systems, because they are fantastically good at telling you how most people did a search loop the last time. What they're terrible at is saying, and how do I adapt that search loop to the particular circumstance of what I'm doing right now? And it says, well, I think if you just do this, probability says if I guess this, that'll probably be good enough. And when you do software that way, you get into an interesting situation very quickly. In some ways, it's worse than a blatant error because probabilistic programming simply means you make a very convincing bit of software that then, because a machine did it, you'll never be able to go back and track and say what was the actual logic behind it, because there was none, because they're just doing it. So you get this scarily attractive thing and said, oh, reuse is good. I'm a huge reuse advocate. This is the best thing about these systems is reusability. You go back and say, like, oh, if I could just reuse that software instead of reinventing it, that's the positive side. The trouble is in the details. The devil's in the details in this one for sure. Is that, yeah, but then are you adapting that with actual comprehension of what you're doing? Or are you just mindlessly saying, follow the probabilities, follow the probabilities? And if you follow probabilities in software, you are going to introduce some extremely interesting errors that are going to be very hard to track down. I would make the assertion that what we're doing right now to our software, with heavy use of software in some industries that is being generated by these LLMs, is that we're creating a problem that's going to take decades to unravel. And it's going to have short-term benefits. It's going to say like, oh gosh, I could fire my whole programming staff and look at the software I did. And individual examples, people say, I can just take a picture of my screen and I get the software to do that. It's true. But if you have to distribute that software to 1 million people, you have a catastrophe because the errors that didn't bother you for one person for a few times then get amplified. So we have to be very, very careful about where you're using these things. There's an end user modification how these things are deployed for software that needs to be there. You know, just like your dot print, your printers, small printers in the end work out well. Small uses of this AI for people who are not familiar with software, that can work out well. But when you get back to the infrastructure side, to the internet itself, you got to start being very, very careful. And in general, you keep going back to it. These things always add some errors. Now, this is my, you know, one picture summary of where I think this thing totally went south. And that is an interesting combination of Hopfield's work. Hopfield, if you look in the lower right side of the slide, he did work on what I would call an improbable emergence, the idea that something could pop up that just is statistically impossible. And when you talk about enzymes in biology, you're talking about improbable emergences. The two cases that are listed in the Nobel Prize were that he showed how a bunch of molecules just randomly running into each other, slap, whack, whack, and some of them look like they're the wrong kind of molecules. He showed how those molecules nonetheless could mediate an almost perfect transfer of an energy electron from one molecule to another molecule, which, as you can guess, is extremely important if you want to do things like I'm doing right now. That's the basis of how we move around. But the mechanisms for doing it are completely, to this day, incomprehensible to us. We don't understand. I won't say, maybe that's overstated. Maybe people have done some good work since then, but I sure haven't seen it, in which they say, how exactly did that work? How did you get a bunch of random things in thermal chaos at all sorts of, you know, look at one of these videos of all the things going on in a cell, you get some idea of what I mean. How does all this random motion turn into what we think of as a precise mechanical transfer? The other paper that Hopfield did, same year, 74, was on verification of DNA reading. Make sure the information is being transferred. Same idea. One case you had power being transferred. In this case, you have information being transferred. And there are some mysterious things about how that happens that, again, we don't know that. And Hopfield was very good at pointing out, says, this is strange stuff. This is really odd stuff. How does that smart capability pop out of these chaotic molecules? So you get this thing that all of a sudden the improbable is what happens. And of course, this is the fundamental basis of life. None of us could be here. We couldn't be having this conversation. We couldn't have these computers if down at the molecular level, these kinds of ridiculously absurd coincidences happen all the time, because they're not coincidences. They're designed, but not in the way that we make big machines. Okay, So that was Hopfield's background. And when he uses the word emergence, he tends to use it in that fashion. So fast forward 8 years, he's starting to work on the mechanical analog for neural nets. And anybody who thinks that artificial neural nets are a good mimic of actual neurons, I I could give you a list of, or just from from meetings I've been in recently, I could give you a list of references, this I don't know, quite long, on why that is incredibly naive assumption. The mechanical models that we have for neurons to this day remain rather superficial, to say the least. So they're interesting devices, and they do that. So Hopfield jumped into it. He kind of though took them pretty seriously. He was saying like, yeah, these are pretty, the knowledge was not as good at that time also. So he took them pretty seriously, saying, yeah, this is a good model of how neurons work, and went with that biology assumption. So when he talks about these networks doing interesting things, that's kind of where he's going for. He's saying like, yeah, just like I saw back in 74, these emergences, I'm kind of thinking that these neural nets or these mechanical models of neural nets also have some kind of emergence. I think a lot of people would agree that networks, neural networks, the actual biological kinds, certainly have some kind of improbable emergence, or we wouldn't be creating and thinking things. So it's got a good point. Now the question is, are the models he was using really that? And the assertion is, which I would strongly stand by at this point, in fact, the more I get into it, the more interesting it gets, is no. What he actually did was he invented a holographic algorithm that uses bits in a computer instead of emulsions on a film. And I would put it that bluntly, that just as you see this picture of these holograms, which for some reason kind of faded in the last couple of decades, maybe because we got too many of them on our credit cards these days. You get the little hologram on a credit card these days. But holograms are really impressive bits of data organization. They have some amazing capabilities. And there's no fundamental reason why, if you have a big slew of bits, and they may or may not be organized as real numbers, it doesn't really matter. Well, it does matter in terms of the details, but the bottom line is it's a bunch of bits. So I go to these server farms not too far from me. There's an enormous number of bits. And the question is, well, what if you interpret those bits as an emulsion, as a medium through which I send information and I make use of holographic principles? What could I do? Now, Hopfield does not seem to have been familiar with holograms. I wish he had been. I wish he had been, because I think what he did is he actually came up with a superb algorithm for creating digital holograms. In fact, this is his algorithm. And you notice, I'll just point through the terminology, which I've highlighted the blue, but pseudo-orthogonality is a result of the algorithm that he describes here. And I want to go over this algorithm a lot more than I have so far, but from the looks of this design, if someone had presented me a problem, said, how do I go about pretending that my database is a photographic emulsion and then holographically store information on it, from what I can tell, this gets darn close to what you would have to do, at least as a first step for doing just that. He's doing the proper thing of coming in from different angles and relating these things to each other. He's using the back propagation ways that had not been done before. But I think without realizing it, he created an extremely clever holographic emulation algorithm, but he didn't interpret it that way. And I think this algorithm that he came up with should have gotten a Turing Award. This is good stuff, and it has some nice potential with that. So, in a nutshell, there's an interesting reinterpretation of good work, but it was then interpreted in a quite different way. Because again, Hopfield was coming from that biological, magical emergence viewpoint. So he was looking for more emergence. He was looking for, say, wow, does something pop out of this that could not have happened otherwise, that would be improbable? And you can just tell that this whole paper has that focus that says, so where's the improbability coming out? Where's the unlikely emergence coming from? And I'm going to do, actually, I'll get back to that point. I'm going to do a little bit of a tangent here because I just said he's doing, it's not a tangent, it's actually the main theme of what I'm talking about. I've asserted that he has done essentially a hologram. So what's a simple way of understanding a hologram? Now, what I would assert to you is that they're easier to understand than you might think. And the analogy I give, if you have two people, you have a pond, they both toss rocks in the pond. Doesn't matter if they toss them in at the same time, slightly different time. The point is they both make waves, and the waves go out and the waves cross over. And without getting into too much detail about it, there's just a deeply fundamental aspect of nature. This goes way into the physics, that you have to have this duality, that things can go, they talk about the location momentum duality, that's one of these. Energy time is another, but it also just much more mundane things. Anything has a wave representation, anything has a particle representation. And throwing those rocks into the pond create these waves that overlap in our space, so it looks like a mess. But actually, those waves wind up encoding the particle almost perfectly, saying, here's where it was, here's where it fell in. And you can kind of see it. You've seen a pond wave, you probably witnessed. You see a wave coming across the pond, you say, oh, something must have fallen in over here that created that wave. So you see it and you go like, well, could I make use of that? And it turns out, yes, you can make all sorts of use of that because they have this duality between the wave representation and the particle. Those waves capture an enormous amount of information about what happened to that particle. They can overlap in very strange ways that seem odd to us. Or do they? Because have you ever tuned around through some radio stations? You tune to one station, tune to another station. Did you ever think that all of those electromagnetic waves are just one giant mess of electromagnetics going through your area? Because they are. I mean, all the waves are interacting with each other. They're messed up. They're one interacts with another. Just like this picture here with the pond, they're all a mess. And yet, all you have to do is put your radio onto that one frequency and say, this is my criteria, this is my dimension, this is my axis. And all of a sudden, boop, out comes all the information that you thought you had lost. And this, again, is this very deep physics principle of this duality between waves and particles. You don't lose things, even though they wind up overlapping in the other side. When you hear about superposition, if you hear this on quantum issues, or of course in quantum computing, superposition is a huge issue. This is another aspect of that. You can't have superposition without a wave interpretation, which is something I think they kind of miss when they talk about qubits and stuff. You want to realize that it's not just the qubits. This wave feature is a part of it, and you can't discard one without the other. One of the features of these that I think is intriguing, especially from this perspective, is there's a naturally Hebbian approach where you reinforce things. You talk about this in neurons, but it also happens in nature. So waves that reinforce in the same angle in a holographic structure also tend to reinforce. So I'm sure there's some cute phrase someone could come up with, waves that splash together. I have no idea. I'm sure there's some equivalent phrase you do with that. But these waves naturally encode ideas like content-based access, because like in the thing, if you get near a pond and you watch some wave structures, the waves tend to pop out. You've seen the rows of corn, like where you get to a certain angle, all of a sudden, chink, some kind of pattern pops out. Very much the same sort of thing, because that is a wave occurrence also. You have a regular periodic appearance, and certain angles bring access to that particular perspective. So all of these things have just really neat properties. So you're getting compression, because if the data is all very similar, if you drop several stones in a row in a certain sequence, the wave patterns recognize that. So, oh, you're just doing the same thing. That's just, I don't need to put a lot of information in that. That's just the same thing over and over again. So you go there and you code that in, and you get this marvelous compression. So things that are very similar in how they do it wind up in wave representation also to be very similar. You get criteria of nearness, because if you're just a little off, you still get part of the information, and you can actually kind of steer yourself right back into it. So you have this nice nearness type approach. Fault tolerance is absolutely inherent, because you don't have to have all of your information stored in one spot. You don't have just one little spot on the, can I use this? Yes, I can. So if you have a flaw right here, a flaw right there, or a flaw over here, you have another rock sticking up, or you have a tree stump or something. It doesn't destroy the pattern. It will do some damage. There's always going to be some loss. But because your location is all in all these places at once, it tends to be very fault tolerant. So this is a nice thing about holographic storage. Now, here's where it actually gets more interesting. Pond is just 2 dimensions. That's boring. 2 dimensions, that's not much. You can put points on there, so you have a bunch of points there. But there's another question you have to ask is, well, this wave idea seems to be pretty tolerant. What if I start getting cute? What if I do a little cutesy thing where I start making the stones and the vibrators, and they vibrate with a very specific pattern, not that different from what I was talking about with radio waves. So you could have, for instance, 2 wave patterns superimposed on the same stone. And just like with a radio, you can tune into one frequency or tune into the other for the same wave pattern. Why not do that and figure out that, oh, I'm tuned into this pattern, and you're tuned into that pattern. They're both coming out of the same radio transmitter, but you don't care. It says, no, I can still tell them apart. We have a different pattern coming this way. The ones here have one structure. The other ones have that. Then you could overlap these coming from the same things. And again, we do this all the time. This is how we get radios. This is how we get radio reception. But it becomes powerful here because it means that you can have not entirely arbitrary, but fairly arbitrary patterns that just generate unique dimensions of information. So this 2-dimensional structures suddenly explode. You go like, oh, well, I have a lot more than 2 dimensions. I have start with 4. I could have 8. Now you say, is there a limit to it? Yes, of course there's a limit, because sooner or later you're going to get too much information stuffed onto these little wavelets, and it's all going to start blurring together. When you're talking about radial domain and you're talking about your Wi-Fi, you call that bandwidth. You have a finite bandwidth. And for the same reason, you're saying that, yes, I can code this scheme and I can make a lot of information out of it, but there are limits. Still, this is a powerful technique, because it means that all of us running around with our cell phones can all be using the same radio towers and all the time and using this. This is one of there's several different methods too. One of the 2 major methods, called code division multiplexing, is just this, is putting arbitrary patterns that have been carefully selected. One of the earliest versions, Walsh paper, I think the Walsh paper is back in 1923. So this has been around for a while. So you get the patterns, you get certain patterns allow you to do this better, because they come out nicely pseudo-orthogonal. And remember that name from Mack and Hopfield, pseudo-orthogonal. Interesting. So let me suggest a rephrasing of the Academy Award announcement. The Royal Society has decided to award the 2024 Physics Prize to John J. Hopfield and Geoffery E. Hinton for fundamental discoveries and inventions that enable machine learning. What's machine learning? Machine learning? Really? Is it really learning? You're just stuffing. How about we say instead compressed holographic data storage? You know why? Because that's a less confusing way of describing what's actually happening. You go back to Hopfield's nicely holographic algorithm, he's saying like, okay, so we need more data storage to do this. His ratio, I think, is about 0.15. So you have to have some extra data, but then because he goes through this in some detail. So you have to have that. So you have the redundancy, but then you actually wind up having this nice property of fault tolerance and of some of these other features in your data storage. And it also compresses the data. And it also allows things that, look at from different angles. And foundational inventions that enable holographic storage with artificial neural networks. Are these really neural networks? Nah, not really. I mean, they're similar. They got certainly can be modeling some aspects of how they are, but they're really more digital interaction networks. How about if we call that with pseudo orthogonality of high dimensional data that is created by these networks? And I think that, again, is a better description of what's going on. You're getting compressed holographic storage with this beautiful little algorithm Hopfield came up with, which imitates some of the characteristics of how holographic wave data is encoded. Here's where the problem comes in. Because Hopfield was very focused, and I think, and reasonably so, he had seen and documented and beautifully covered spontaneous emergence, or this unlikely emergence, in quantum biomolecular systems that have been optimized by, your cells wouldn't work if they weren't optimized for this. So these are actually complex little machines here. So they're highly optimized, but they still come out with this improbable behavior from random chaos interactions of molecules of some property you want. So he started postulating, this is the quote that I think captures it best in his paper, the bridge between simple circuits and complex computational properties may be spontaneous emergence of new computational capabilities from collective behavior of large numbers of simple processes. If any of you who might be familiar with the history of biology, when you see that part what I outlined in blue, that should be a little bell going off, because until 100 years ago, even certainly in the 1800s, there was this concept called spontaneous emergence of life, of spontaneous. I think the last representatives were the silver eels in England. They actually have no sexual organs. They came out of nowhere. Nobody could figure out where they come from. So there was a persistent belief that they just emerged spontaneously from the mud. And I think the silver eels, because they were so incredibly hard to figure out what was going on, they have 5 different life forms. That's why they're so hard. Was one of the last ones to die. So people just thought that, life can just pop up, just blink like that. Spontaneous emergence, you have to be very careful with, because it has a strong connotation of that idea of kind of a magical capability that randomness just sometimes decides, and I'm going to do something. What he really did, and I think you can document this in remarkable detail, was figure out a way to generate these almost orthogonal vectors in a high dimensional space, which is what you need for a Hilbert space. Every angle you look at a hologram, you need to have essentially a different unique axis. Now you have them blending over into each other, but you have to have this high dimensionality. And that's what he really devised. And the trouble is that the data remains data. Data doesn't emerge. Data doesn't suddenly say, oh, I'm decided to become more data and do that. Even if you have a lot of computational process around it, the data itself can't do that. The data is just dumb. That's the kind of the nature of we want data to be dumb. We don't want it going on morphing itself. So his innovation, I think, was this auto generation of these Walsh-like pseudo-orthogonal codes. And by the way, I think he may have had some, what you call a limited form of emergence in that, because this thing with the back propagation, he was able to get it to kind of organize itself into the axes. They were competing with each other, fairly straightforward kind of thing, like, well, Dan, what's the frequency? George, what's the frequency? And they kind of negotiate with each other and figure out which one, well, I'm going to have this unique frequency, Dan's going to have that frequency. So they all eventually resolve the question of what's the frequency, Dan? And yes, that's a reference to it for old timers. So what is emergence? And this is where it gets important to make some distinctions. This is a word that has at least two very, very different meanings. Simplifying emergence reduces and discards complexity. It still leads to very interesting effects. Those effects may, in fact, be powerfully useful in all sorts of situations. Temperature is just the obvious example. What is temperature? It's an enormous number of very complicated molecular motions that just average out into a single quantity that is far too simplified if you get down to the details. I mean, if you start working with individual molecules, you can't use temperature anymore. That just makes nonsense at that point. But for larger sets, very, very useful. Does it always work? No. Sometimes there are concepts where the idea of temperature doesn't even make sense. You can't really define it. Which, by the way, I think you can make some interesting arguments about relativistic spacetime, that sometimes you have to be careful there too. It's not always easy to define exactly what you mean in relativistic situations. Implausible emergence is where you beat the odds. And I think that's a very important distinction to make. Temperature does not beat the odds. Temperature just wipes everything out. Implausible emergence is what Hopfield looked at with biological systems, where they're somehow able to do these things, figure it out, and come out with a really powerful outcome. That's good. You got to make a distinction between these two, because if you start talking about emergence and you're talking about one of these, and you're actually talking about the other one, you're going to get in some trouble. Now, on the specific issue of Hopfield networks versus, and by the way, that's not a very good Hopfield net. I should have, yeah, if I did over again, I'd draw that as a Hopfield network. It's just that's a layered approach there. But same general idea though. You've got networks where you've got very, very classical connections where you're transmitting very, very stubborn little bits who engineers work for their entire lifetimes to make sure that bit doesn't change when it gets transferred or stored. And then you've got on the other side, you've got these quantum issues. There's no networking going on there, at least not any network we can figure out. They're local little beasts that at a very small level figure out how to do things in extraordinary ways. And we have some inkling of how it happens, but if you've ever seen either quantum physicists or conventional, anybody with a computer trying to model quantum mechanics, you will find out very quickly that if you get over about 2 atoms, it starts getting difficult, maybe 3. Now look at these DNA molecules, these mechanisms that handle DNA. These are tens of thousands of atoms. We don't know how that works. We can pretend we do, but we don't understand how that works. We can't map out what's going on at the physics that applies at that level. So we use a modified mechanical model where we can kind of say it's sort of like a machine. Yeah, except when you get into the details of the actual final interaction, there we always get in trouble. These are very different architectures. I mean, over here, you've got these hyper-classical, hyper-connected things going on here. And over here, you've got these very quantum, very microscopic things going on here, showing true emergence in that. So you want to be careful. You want to be careful about saying that these are in any way similar systems. This is almost an aside, but I always like to put this out. I think we have a very unfortunate focus on what we mean by bits, especially when we're talking about quantum computation. How do I put this bluntly? If you take quantum mechanics, strangle it to within a nanometer of death, and then allow just a little bit of a tweak room so it's not totally extinguished yet, that's a qubit. Because qubits are modeled on one of the most classical concepts in the universe, which is a stubbornly persistent value of 1 or 0 that lasts forever through space and time. And you have to do an enormous amount of work to make that happen. If any of you out there have ever worked or touched the semiconductor industry or some of the circuit designs on how you make a bit reliable, you realize that the idea of storing a stable bit function of 0 or 1 is not trivial. It takes machinery. It takes concepts. Even the classic example from quantum computing of electron spin, people forget that the electron spin has no meaning until you put a gigantic magnet around it. And that's your real bit. the fact that it has a spin doesn't mean anything until you make it into a bit. And that means you have to add machinery. So what we do with bits, which we focus on as our center for doing quantum computation, which is that there's a remarkable paradox there. So first thing we do is strip out any trace of quantum interference. Make sure that nothing quantum gets into that bit. Just make it solid as granite. You want that thing rock solid. When you look at Hopfield's 1974 stuff, whatever is going on there, by the way, those things are not blue and red blood cells, they're orbitals. So, pardon I looked at that myself, but it looks more like blood cells and weird colors than anything else. But the idea is quantum orbitals. We have a general idea what they are. But when we get into the details of their interactions, they are doing something that takes us an enormous array of computers just to figure out a small bit of that. But instead of tossing that out like we do when we create bits, the quantum emergence at the cellular level, where we get these very improbable outcomes, is somehow working with all that chaos, because these are chaotic systems. And you've got quantum chaos suddenly leading to a really interesting result. And we don't usually think of quantum computing that way, but I would say we should. Manin did back 1980. He immediately discarded it because he was so enthused about computers, which is unfortunate. But he certainly pointed out the idea that there's incredible amounts of computation going on in just the simplest things, and life in particular seems to do a better job of making use of that with its emergence. So endurance versus emergence, not the same things, not the same things at all. Hopfield said spontaneous emergence. I'm going to pick on him again for that use of that terminology. If you especially put it in the context, which the Nobel Prize announcement does a nice job of doing, really, he was talking about these implausible emergences, which is new physics. That is, if somebody can figure that out, that is worth a dozen Nobel Prizes, because we still don't get it. And we have such an incredible computational time at getting good models for that. So, I mean, yeah, if you could, what he did was confine the problem and point out that it existed, that this stuff existed. And that was beautiful work that he did. But he puts a lot of biological terminology mixed in with his computational designs in his 1982 paper. And it really looks, as far as I can tell, somebody could go out and ask him, that he thought he had found a new implausible emergence, that this was something that should not happen, but does anyway. So if you look at that, though, in combination with his own equations, his own analysis of the complexity, because he did look at this as an information problem, he was perfectly aware that these were lossy networks. They weren't perfect. He had figures where he shows how you push it too far, you get this much of a loss. So he was aware of that. And that too is a deep aspect of this quantum duality I talked about earlier. This it's not just quantum, it's in life in general. If your wave is limited in size, you're trimming off some of the accuracy of the bits. As simple as that. So if you have an infinite pond, you have an infinitely precise bit. But most ponds aren't infinitely big, so you lose something. And this is one of the dangers of holographic encoding. And Hopfield was aware of this. I mean, he like I say, he puts in charts and he did some tests and had some good results showing what was going on with that. The trouble is, and this is where I think things went wrong, is he didn't quite recognize, doesn't seem to quite recognize that the capabilities were coming from his encoding strategy. That he came up with this brilliantly clever encoding strategy, but he was not a hologram. He was not a holographic guy. He didn't think of it that way. He describes the properties of holograms beautifully. Like you can take half of the hologram and still have most of the data. So he describes the properties, but he doesn't make that cross-link. Hopfield in 1982 on those lines said additional emergent collective properties include some of these, blah, 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 blah. And again, I would do this little correction here, or suggested correction, but I would suggest it very strongly. Emergent collective is, emergent especially, is a really loaded term in this context. If you instead say holographically distributed data properties, suddenly it pops into a lot of clarity about where some of these things are coming from. Generalization is from that near axis access of the encoded dimensions in your hologram. Familiarity is because you already have these existing data accesses, so it gives you a classifier. You can say, oh, this new wave coming in is just an example of that. We've seen that wave before. We know about that wave. That's the wave that in an LLM is the cat wave. That's the cat axis. That's you identify it's a cat. I'm suggesting that there's an actual wave structure in the bits as you go down in there. I think that's one of the areas where there could be some very interesting research and saying, well, what's the wave structure? Instead of thinking of it in terms of abstract numbers, think of it in terms of bit structures. Categorization, slot in new data, goes right in there. Error correction. This is one more than anything else where Hopfield seemed to think that that was emergent because he'd seen that in like both of those cases I mentioned earlier. He had seen error correction, the ability to tolerate noise in the transfer of the electron. He'd seen the ability to correct errors in the translation of DNA in the other paper he did that same year. So error correction to him was an important emergent property, and I think that's where he kind of flipped over and said, "Oh, this too must be an emergent property." But again, the difficulty is that if you don't recognize this is holographic data format encoding, then you will come out with a more exotic explanation for it than you should. Because he's really just saying that individual devices don't matter, which he actually does say exactly that. Individual devices don't matter, it's tolerant to that. Yes, because it's holographic. You've distributed each of the data items over a larger sequence. He also brings up something called time sequence recall. This one I want to look at more closely because I think he's judging by his references more than what he says. I think he's linking a little bit too much into the real neuron behaviors in which we have loop behaviors and all sorts of interesting attraction points. And I think he was climbing maybe a little bit too much because I don't really see his structure supporting that very well. But he may have just been talking about the correlation between the axes. But I would like to look a little more closely at that one. But either way, the bottom line comes out and says, if you describe this as how he created a beautiful new way to do a data structure with properties that made it fairly easy to compute. It was still difficult for that time. I think you just get a lot clearer idea of where these behaviors are coming from. Now, 2023, let's jump to the present. If you look at, there's lots of great work online, looking at these systems, saying, where's the data? Where is it at? What's going on? What's the physical meaning of some of these systems? This one particular, you can find this online. I did not give the link there, but it's in the paper. So if you look at the paper version of this. But why superposition in fact-finding? Fact-finding, so that when it says fact-finding, he's saying like, where are the facts? Where do we find the facts in the LLM? Because it's not easy. They're not just sitting there at one spot. And of course they're not, because they're holographic is what I would say is the counter in that. And you see this coming out when the superposition topic comes up. It just frustrates people. And I would suggest that, yeah, it is superposition, but look at it more from the physics viewpoint, from a wave particle duality viewpoint. And I think that might start making a lot more sense. You're having coding spread out throughout your memory, and you're simply tuning in to the different directions of what the information is. I think that could give a much more clarity to some of these issues that are still driving people a little bit buggy with this. Here's an example. This is from the same group. They got marvelous work. I highly recommend, and that one I did give a reference to, on the different structures that emerge inside of LLMs. And this one just particularly fascinated me because you have these features where if you took, this happens in atoms, by the way, if you took a bunch of electrical charges and say, how do I spread them out in a sphere so they don't run into each other, so they interfere with each other in the least, you wind up with these different structures. And my suspicion is that some of this has to do with the self-encoding concept, that the idea that Hopfield came up with a structure that self-encodes different unique signatures for the different accesses. He doesn't put them in explicitly, So it winds up being encoded. But I'm pretty good chance that when you're getting this level of geometric structure emerging spontaneously, that you are actually getting into the coding aspect of how these vectors come into existence. Now, blunt part. This usually would have been just, we all like to be optimistic. Every one of us likes to think we found something new and something really cool. And I think that's what happened with Hopfield in '82, is he said, oh, this especially like fault tolerance ability, and that sure seems like one of those cool emergences that I saw in the other thing. Um, the blunt way of going after that, though, is what Feynman, with his typical Feynman pointedness, called cargo cult science. Cargo cult science is very simply that you look at the superficial resemblance, and from that you think that you are actually understanding what's going on. The specific example that Feynman gives is people would make a little, on some of the islands where cargo planes had come in, they would make little wooden headsets with bamboo antennas, in the belief that that was the way you invoke to get a plane to land, to get this marvelous thing that had been happening for a while during World War II, where all sorts of new items are coming to these very remote locations. We do that, and this is what Feynman worried about. He warned us about this. He said, this is cargo cult science, and it's a lot easier to do than we think it is. It is very easy to get our hopes, to get carried away with us, and we see a superficial resemblance. And if we see it in something like, say, a global network of digital circuits, the next thing you know, we might be thinking that, well, yeah, that's just chaos and it's disorganized, but maybe an intelligence will emerge out of it spontaneously anyway. And unfortunately, that was the critical point that Hopfield encouraged. I would assume he's not the only one, but he certainly made a sufficiently powerful argument for it that the Nobel Committee noticed it. And the Nobel Committee accepted it as a real emergence. And that is very unfortunate, because what really was going on here is something, I think, much, much simpler. It is still extremely interesting. It deserves a Turing Award. I don't think it deserves that paper, I don't think deserved a Nobel Prize. I could argue that his other papers maybe did. But the fact that they focused on that one as the center point gives people an unfortunate impression that just like the mud produced the silver eels in England, the dead data of our global web just might spontaneously produce an intelligence. And this is not true. It's just that the two are far too similar. I mean, the eel and this intelligence side. And how many people have you met that are terrified that the internet is suddenly going to become spontaneously intelligent? I was one of them. I think I had that view for years. And that's one of the reasons why this is so fascinating. Is I got into it and said, like, I was believing a bunch of hooey. It's not that there isn't a danger that somebody's going to create an artificial intelligence someday that might be smarter than people. My guess is more likely to just be incredibly unstable and destroy itself almost instantly, and then we'll slowly get it more stable. But I'm not afraid of this anymore. I'm afraid of this doing stupid things with the internet. In fact, I'm so not afraid of this. I'm like, this is just cargo cult. There's no reality to it. There's no spontaneous emergent to it. Some entity is not going to pop up and suddenly take over the internet, but people might. So this is why I say the Nobel Physics Committee, to me, this was an egregious error. And the reason is they essentially awarded a prize for non-existent physics. And in a time in which people are going berserk on just that physics. But again, we're all human. Nobel Committee has seen all this emerge, these server farms and all this thing. I think they were a little too optimistic too, and they were forgiving, just like everybody else is. Oh, if we train it just a little bit more, maybe it will suddenly do what we want. A little more positive side. 5 recommendations for the future of LLM research, because goodness, we've certainly put in a lot of money on LLM research already. And all those server farms, we're in the $1 trillion range here. And they do useful things, but they don't suddenly become spontaneously intelligent. So first suggestion, get rid of the myth. Second suggestion, this to me is the most intriguing one because I think there's some mileage in this. If all these things is giant holograms with the bits representing photographic emulsion bits, why not use actual holography, which is so what? I don't know. Many orders of magnitude more efficient. Optical holography is unbelievably energy efficient. Bit-based, NVIDIA board-based matrix multiplication version of the transforms that you need to do to accomplish holographic transformation is probably the most inefficient way that you could possibly go at that problem. So if this is actually holography, I'm saying that somebody ought to be paying close attention to the optical equivalent. We have optical holographic memories. There's technology that already exists. Some have been around for decades, actually, but it's never really caught on. Third idea is take those molecules more seriously. If it's so difficult to do the molecules, to compute the molecules, why aren't we doing more about trying to understand how we could compute with them? Our cells do it all the time. Maybe we could do something also. Along those lines, we need to understand this idea of improbable emergence, specifically to counteract what situation we've got ourselves into with these artificial neural nets and LLMs. We can't keep up with what we're doing. We've created an enormous overload of sloppy information and trying to correct it with humans, and that does not work. Final point is I would argue that we need to be more careful with some of our mathematics. We have beautiful mathematics for the subset cases, but often when we touch in these areas about information spread, energy limits, the universe pays very close attention to all those issues in its formalisms, and they are formalisms. The universe does things in very precise ways. The models we use for those aren't always that precise, and probably we should be a little more careful in that. I particularly pick on Hilbert space because it's got some interesting issues. So again, drop this spontaneous emergence myth. Let's get rid of that. It doesn't help if you're in the middle of this doing postdoc research or PhD research on how these LLMs work. Drop this. It's not going to help you. It's not going to help you understand what's going on because it's relying on randomness as having magic properties. And randomness does not have magical properties. It has some very interesting properties, and they relate to, stochastic amplification. You can certainly use randomness, but don't rely on it to just do things for you. One of the points I put out, this is Dr. Sotis in Toronto. He talks about, in fact, he's proposed something called a visual Turing test. Because if you look at how the eyes work with the brain in order to understand a problem of recognition or identification or finding, they have things going on there that are jumpy, that are constantly exploring, scouting, collecting information. This seems to be a better indication of how actual biological cognition works. And I've encouraged John to please write a paper in this. It's a visual Turing test because the current Turing tests, which I've not only used but elaborated on at different points, it's just been gamed to death. It's not doing its job anymore. The power of the hardware has made it obsolete. And again, emergence does not happen if you just keep adding training. This is a disastrous way to think of this problem. because it never ends. All you're actually doing is increasing the scale of the fringy information where the thing goes probabilistic on you and drifts off into nonsense. And then that gets incorporated into the system, and this is the analogy I've used this before, but I mean it very seriously. It is the intellectual content version of the Ponzi scheme. You're always putting off the payment in the future, thinking that suddenly it's all going to work. And it won't. It's just going to make the problem worse. So we need corrections to this, and we need better ways to correct it. Optical holographic models, enormous energy reductions is probably an understatement. I mean, Fourier transforms are so cheap. You can use a single photon to do one photon. Can do fantastic Fourier transforms on enormous objects, including gravitational lenses 10 million times around. That always amazes me. How does a single photon do that? We don't get that very well, but we see it. So it's an observational fact. This is not some hypothesis that a single photon can be curved by a lens 10 million light years across. Well, if one photon can do that, that's a pretty good energy efficiency for the scale of what you're talking about. Possibilities like that definitely exist. And of course, they are as literally as light speed as you can imagine. You've got optical storage medium out there, so it's not a blank. You don't have to start completely from scratch. I think LLM people, if using their expertise and like some of those marvelous figures I just showed a little bit ago, use their understanding of the structure of the existing LLMs transformation process and how the transformers work. I think they could give some really good insights on how this could be made into an optical conversion. So I think it could be a really interesting interaction there. And translate those structures into coded waveforms. Molecular research, computers research. Yuri Manin, again, he mentions this idea, and it was in 1980, and physics was just fascinated by information in that time period. They were just absolutely entranced by it. So they didn't see all of the electrical engineers working so hard to make the bits small and make the bits really stable. They didn't see any of that. All of a sudden, everybody's seen these powerful new computers coming out. And I think it gave a biased viewpoint about the naturalness and the simplicity of bits, because they're not simple. They're not easy. You have to work hard to make them. They're hyper classical. By that, I mean they're so self-observed and pinned down that you can't change it. That's the idea, is you want it to be persistent. So bits. And if you think about that, if bits are machines that you have to work out that hard to make it, then you want to be careful about assuming that they are the fundamental fabric of the universe, because you've just made engines into the fundamental fabric. Don't do that. Get something simpler. So Feynman had a better idea of the quantum computing. He actually was close to the idea that said we need to borrow this stuff. We need to. Yeah, he never introduced the idea of a qubit. He never went to the binary thing. As soon as you get the binary thing, you've gone hyper classical, and then you're just backing off just ever so slightly so you can make it quantum. No wonder we have to cool the machines down so cold, because it's hard to make a machine quantum. They're big and they're classical. So molecules don't do it that way. We don't know how we do it. Enzymes, Bose condensates. Now those have been used recently for powerful sensors that can detect gravitational differences over a small distance. So Bose condensates might have some interesting potential for that. How we're going to do this, we don't, I think just facing the fact we don't understand what improbable emergence is. I think there's a very good chance that until we understand features of quantum mechanics at the molecular level better than we do now, because right now we don't do well. It just turns into a combinatorial explosion, and we just wind up not making good progress. So if we can understand that better, there's got to be some interesting physics. Side note, then in preparation for the last slide, which I'll just suddenly wrap it up. Um, the Hilbert spaces don't model dynamics well. This is a beef I have. I mentioned it earlier that we have to be careful with mathematics that is overly simplified. Now, you think about this. This is almost like this can be a culty thing too. If you have an extremely simple equation, do you say, that equation probably is oversimplified and I probably should look for a more complex context? Too often the reflex is the other way around. It says the math is so simple that I think that's the perfection. That's where the universe is. The universe starts with there's a whole school called S matrix from back in the 70s. But I think the math is the actual heart core of it. The trouble with that is you can't do that experimentally. So if you're building real devices, it never works out that way. There's always some complexities to it. In the specific context of what we're talking about here for LLMs, the Hilbert space model is a great model for state space because these things get enormous numbers of dimensions. That's what a Hilbert space is. It's just saying a space with a very large number of axes, orthogonal or pseudo-orthogonal to each other. And my point with this slide is an oddly simple one, which you've heard how explosives are not allowed to go through tunnels. Trucks with explosives are not allowed to go through tunnels. Why? Because when you're in a one-dimensional world, an explosion goes off, the full strength of the explosion propagates down the distance indefinitely. And that means everybody is dead, not just the person in that. The entire tunnel all dies. So this is an example of dynamics based on dimensionality, which is something that gets oddly skipped over. I don't really understand why. The color force actually is an example of this. Color force, if you stretch it, is like a bungee cord. It just keeps adding energy at a fixed rate until it breaks or something else happens. Pond waves, they dissipate as 1 over r. So this time, if you have an explosion there, you got a chance of surviving over here because, at least the energy has dissipated. And the farther away you are, the better off you are. Three-dimensional space, electric force, gravity. We have a 1 over r squared situation where things fall off pretty quickly. And you have to take that into account if you want to get an accurate accounting of the dynamics. So let's say we build a LLM with an enormous number of axes, and so much so that we can say it approximates infinity. If you look at this and assume that everything's fine for the interaction between the axes, you're going to be in for a surprise because the dissipation rate for an infinitely dimensional space is, well, essentially it's null. The dynamics don't travel. So if you try to send a signal out there, everybody's in darkness and saying, I can't send it. Every signal I send just dissipates, everywhere like that. Now, even though the spaces that we use in LLMs are abstract spaces, they still have real energy relationships and limits. And I've heard people talk about how the actual operation of these space, I don't remember, someone made an interesting comment just along those lines. It's more like a lightning strike, something you suddenly subset the Hilbert space and you go to a much narrower pathway going. And that just makes sense from a physics information viewpoint, because these things don't, you have to be careful about modeling dynamics with overly simplified static only models. And however respected Hilbert spaces are for that, they're not ones that you want to just casually think you can use for dynamics, which is a problem that faces some of these. So, and that was my final point, is just energy-aware formalisms, energy and info-aware formalisms. I think we need a little more sophistication in some of how we deal with these. There was a talk I was going to give about fairy dust, and that one actually is nicely blent too in a whole different way. And everybody's here probably, if it's quantum computing, you've probably seen a black sphere. Have you ever noticed that the bottom of the black sphere has like digits, really, the numbers really close, quite close to each other. So like 0 and 1, real close. If you go to the top of the black sphere, they're infinitely dense. The numbers are infinitely dense at the top. And we think we said, well, yeah, but it doesn't matter. It still lets me, track the binary nature. That is true. But you want to be careful about infinite assumptions about information. Why? Goes back to the same thing I said earlier. Bits are machines. So if you want to model the actual universe as opposed to some abstraction that is not really the universe because it would be infinitely expensive energetically, then a block sphere is not a good model for a qubit because it represents an unreachable situation in which you have infinite saturation at one end and the other. Quaternions, I love quaternions. Quaternions are a much better way and probably closer to how the universe does it. So, we want to keep our models close to how the universe actually does things, almost like a duh, but why not? Because that's one of the reasons why quaternions have taken off in so many simulation areas, because they seem to be closer to how the actual systems do it, and that makes an interesting thing. Another example of that, this one is actually, this is something I took off time from doing this, but this is Einstein actually redefined space in terms of clocks back in 1911. Then he went over to general relativity and abandoned that. And in doing so, he actually limited the definition of space. So as you don't just set up a set of coordinates, he actually put time limits on the definition of an inertial frame, which is just absolutely fascinating. And something which I wish he had worked more on. But again, he went off to something called general relativity, so he never followed up on his own models with that. But I would make the assertion that especially when we're doing these stressful limits on information, we need some better formalisms, and this would be an interesting thing to do. And I believe that is it. Yes. So I think it's time for questions, if there are questions.
Yeah. Okay. Just checking. Did anyone have any questions? Did anyone just want to put their hands up? Just ask directly. Just putting it out there. Okay. Guess not. Yeah, there's some questions in the chat, Terry.
Okay.
Yeah, so Katano Pang asks, why are we trying to assume that AI is omnipotent, free from any possible error?
I think that's a good point, that there's an assumption that if you can produce a system that shows emergence of intelligent-like behavior, that with sufficient hardware behind it, it will suddenly start correcting itself at a rate that a human could because we have much slower neurons. So I think when people come out with that idea that somehow an AI is going to be perfect, they're reflecting that idea. They're saying that, yeah, because of the amount of circuitry and speed, they can do things that. And of course, the whole point of my talk here is that I think that the whole concept is wrong. That all we're really looking at is chaotic bit systems. If we want to make an artificial intelligence, it's going to be hard work, really hard work. And I know some fantastic researchers who are working on just that kind of stuff, and the depth of what we don't know about real intelligence in real systems, in real biology, is just astonishing. We got this idea that because somebody invented these neural net analogs back in the 40s, it was all the way back in the 40s, that we understand them, and we don't. So I think there's interesting potential, but they're not going to be perfect. And this, to me, this is actually a relief. I was one of the people who at different times said, "Oh man, what if one of these things takes off? Are we going to get this Arnold Schwarzenegger scenario?" And I have stopped worrying about that. I'm going like, yeah, I'm much more worried about how people use computers. And someday, I think we'll get to more intelligent ones, but I think it's going to be a long haul.
Great. Another question in the chat. For the wave particle duality, can you explain what you mean by the wave encodes the two particles, including the stones?
Okay. It doesn't include encode the stones, but if you have a pulse where you have like you took your finger and you'll snap, you hit a water surface, and you're considering that the entity itself. The duality is that you have a location on the surface. You have some, just like we think of it, as a location on a map. So you have that map, but when you tap it like that, if you have the ability to convert that into a wave, you get this spreading wave, which we've all seen. And the remarkable thing about that wave is it fully encodes that original location, but it encodes it in a very weird way. It has these concentric circles that just keep focusing back. But if you follow the focus, you can see it. Say, oh yeah, it's pointing back to where the particle was. And there are many places in reality, say this is really deep principle. There are many places where you can just keep doing that and you go back and forth between these representations. When people talk about particle wave uncertainty, that is exactly what they're talking about. They're talking about how the wave of the particle, that which becomes an actual wave that you can represent, if you can get it to snap back and turn back into that particle. And the details of how that happens, that's one of the problems, is nobody has ever worked out the full details of that yet. There's some strange relationship on how this flips back and forth. But big concentric circles, they point back to where the original particle was. Now, if you want to get farther into it, it's actually even more interesting than that. There is a two-way duality where every time you have a wave, you can represent it as that particle, but also the particles can be represented in a wave space. And this is where you get into, there's a concept in quantum mechanics called momentum space. And you can remap the entire world into momentum space. And it looks really, really weird when you do it. But it's also a powerful technique on what you're doing. And I say the best I can, probably not that good of an answer, but the duality goes with the fact that waves have a shape that always allows you to retrack, reverse what it is, and come back to the point-like representation.
Great. Somebody also asked, is this information bandwidth limitation not something that happens with quantum computing?
This information bandwidth limitation absolutely is something that happens with quantum computing. And one of the dangers in some of the mathematical models that are sloppy on that is that you may not notice this. And this is not a minor problem in physics because I don't want to get into it too much because many people are very vested in this idea of infinite precision of the models in quantum mechanics. But when you talk about many worlds models, where they say there's an infinite number of universes, that is exactly what they're saying. They're saying that the energy as defined in quantum mechanics does not behave like the energy that we've seen in every example of physics ever done, which is a problem. There's a physicist that I've written to him multiple times on that and said, you do realize that when you say energy, you're not saying energy. And he kind of acknowledged it at one point, but he's very vested in it. And it's not that complicated to point. Nothing we see in the physical universe has infinite bandwidth. Material objects like atoms have enormously higher bandwidth because they got a lot of mass, but it's always finite. And when you get mathematical theories such as the many-world theory, I can tell you the exact line wherever it did it, in which he just went, whee, I don't care. Or but worse, I don't think he understood it. I don't think he got the fact that he was doing something that required breaking the speed of light, that required infinite energy, that required infinite time. All of those things apply to the key sentence in which he said, oh, there's an infinite number of universes every time something changes. And I don't think ever he just didn't get it. He was looking at it from a very pure math viewpoint. I don't think he had much physics background. So he just looked at the equation and said, I'll just do with that. But in every version of quantum mechanics that we can actually access in a lab to get a useful result, there is always a bandwidth constraint. There is always a speed of light constraint. That when you go from one state to another state, it doesn't infinitely change the entire universe, including entanglement. There's one physicist, Asher Paris. Asher Paris, one of the most interesting comments he made is he's talking about the Alex and well, A and B, whichever one you want to do. Someone changes something here on an entangled particle pair. He made the very good statement that you don't change anything over at B. Nothing changes. It doesn't change anything. The problem does not emerge until the information travels at light speed and reaches that point. Then you have a problem in interpretation. But often people act as if entanglement is a phenomena that actually goes faster than the speed of light. And Asher Paris caught that better than anyone else I saw. First time I read that from him, I said, I don't understand what this man is saying, but I really like his point, and I see that it's correct, experimentally correct. But we don't understand entanglement well, because there's an aspect to it that the interpretation must travel at the speed of light, and until you actually get that past that, nothing happens. So we're not modeling that well. That's a piece of poor math.
Great. So in your what is emergence slide, Terry, somebody asked, what is the frequency?
What the emergence is he kidding or not? Because I did make a joking reference to there was a famous episode where a reporter, an anchorman named Dan Rather, a lot of people don't even know anymore. He was accosted on the street and people kept asking, "What's the frequency, Dan?" So I don't know if that's a reference to that. Read the question to me again.
It was George. She was just asking what's the frequency? Yeah.
Uh, I will answer that in a different tangential fashion, which is this. Somehow in Hopfield's algorithm, and this is something I really want to look more closely at his algorithm, I believe he is spontaneously emerging frequencies. I think they're negotiating with each other, and that was the reference where I brought in that thing about what's the frequency, Dan, where the two axes are looking at each other and say, well, what's your frequency? What's your code really would be more accurate than frequency. But what is your code? What is your code? Says, okay, we're gonna put ourselves onto a sphere and push each other out as far away from each other as we can. And that's going to produce an interesting geometry in which you have a good degree of quasi-orthogonality, which is exactly what they're seeing in some of these toy problems with LLMs, which I find fascinating because they, in fact, some of these points are going out to different layers. It's as if they're trying to generate their own frequency, their own code to define that. And it might be where that's emerging from, but that's something I want to look at more closely and see if that is what it is. The point I want to get at, though, is this. If a large chunk of the back propagation on many of our LLMs is actually for the purpose of creating codes that then separate the dimensions, we could short circuit that and say, you don't have to generate your own code. I'll give you a Walsh code. Here, take it. And it would say, oh yeah, thank you. You just saved me about a gazillion watts of processing time or energy cost, because that back propagation process is expensive. So I think there's a potential shortcut here where instead of the different pieces asking what's the frequency, we say to them, says, here's your frequency, here's your code. I will define it for you using more formal processes. And you don't have to go through that mess, because that's a slow negotiation, especially if you have a lot of dimensions in that. So there's another one of the areas where even with the purely digital systems, I think there's potential for considerable energy savings if we look at them as holographic and say that, how am I coding my dimensions with that? So no more what's the frequency. We just go to here's the frequency and see what happens. And my guess is that we could do some nice shortcuts with that.
Great. Um, Another question from John. So the Nobel Prize was actually given for the logic circuit or the logical algorithm?
The Nobel Prize was phrased carefully, and actually, I think they did a good job of phrasing it. Uh, the the justification for the Nobel Prize, the best justification, which is in the announcement, is that these artificial neural nets have proven extraordinarily useful to physics because they can process information at speeds and in quantities that humans cannot do. So particle colliders, oh gosh, weather modeling, take your choice. Any place where these things are controlled and not trying to pretend to be humans, they're incredibly useful. And this is I mean, I supported the research in this. I mean, this is one of the things where at different times people tried to pull the funding out from people like Jan LeCun because it's that's old fuddy day stuff. You want to go with the other stuff. And I'm one of the people who supported said, no, this is good work. But you want to and I completely lost the train of where I was going with that. Okay, good work in that. Okay, so
Right. Yeah, just a final question from Lewis. Lewis asks, isn't IBM using biology for computing?
I think they've had some research that has looked at aspects of that. I don't know about IBM. I think there's some other groups that have used biological aspects of computing. I think the most famous one right now is the slime molds that are able to calculate a pathway. That might be the one you're referring to. Calculate a network, an efficient network, faster than most of our computer systems. So yeah, there's some good examples of where living organisms, simple ones, can do some quite remarkable computations.
Okay. I think there's just one more question. Um, yeah, somebody asked, regarding emergence, could you comment on Phil Anderson's "More is different"?
I'm not familiar. I don't think I'm familiar with Phil Anderson's "More is different." Is this a paper? This is a comment. My apologies. I just don't know I don't know the context.
I don't know either. Um,
The questioner is welcome to explain if they want.
okay, it's fine.
By the way, what was the previous questioning? Because I was talking about Jan LeCun and some of the history of that, and I know I got off track, and I don't know if I ever got to the final answer. The previous question was,
Are you asking about the Nobel Peace Prize question or?
uh, the question right before this one was
Uh,
about the Nobel Prize was, oh, it was awarded. Yes,
yeah.
that's where I got off. It was awarded for all of the very real uses of these artificial neural nets for high speeds, high capacities, high densities. Humans can't possibly take them, and I think that's appropriate in that sense that if that's the thing you focus on for the Nobel Prize, that's good. They did specifically call out that paper that I was grousing about as the one where they introduced this emergence theme. So I that's the part that I wish they had not done because I think that exacerbates an existing problem with emergence that's not there. So that was the part I lost when I got off into reminiscing about some of the issues with Jan LeCun. Anything else?
Great. Yeah, so that is all the questions that we had in the chat. Did anybody else in the Zoom have like a question that they want to flag? Anything that they want to bring up before we wrap it up here?
Can I make it just comment the question sometime? When I read the title of your talk, the word degradation, and
Yeah.
I start thinking, oh, this degradation may be something which erodes with time
Yes.
or damage with time, kind of thing. So I thought that you're going to talk about changes, things will change with time. So your talk was mostly appeared to me that you would be challenging that Nobel Prize in terms of, to some extent, appear to be a bit pedantic. You know, you're replacing the spontaneous emergency with the holographic kind of data kind of thing. So,
Right.
I wonder if you set apart this question, this pedantic issue of emergence, because the emergency could have different interpretation. You know,
Right.
for me, I was thinking in emergency, something spontaneous emergence, something which occurs due to mutations. If you look at biological systems and the evolution of biological systems has been through hereditary and mutations. So I was thinking that whether in the computation side, also you could have these mutations in software as time progresses. And we don't know the outcome of those mutations. Those mutations could either be hardware or mutations in the software. So I wonder what you think about these issues.
That's a great question, and I could have retitled the talk like holographic interpretation. The reason I phrased it the way I did is that was a serious concern. The expansion of the Nobel Prize going for this has increased the likelihood that people will just put some of these LLM coding systems willy-nilly into their systems and produce degradation. It's going to be extremely hard to get out. So there's a very real intent in the system. I think it's just unfortunate that even though they had all those good things that they brought out, which were some really good things, they also put the imprinter of this is a good thing, this is a real thing, on something that's not real. That's not what's going on. I would strongly assert that that's not what's going on. The question you mentioned about the evolutionary part, this seems to be a related type of issue. I would argue that the entire world is a giant digital hologram type thing, and that most of the properties that comes from it are like that. We try to do the software evolution thing, and this is again a topic I've tracked. I've had enthusiasm for it. I've had disappointments in it. Mostly it's disappointment. It never seems to work out the way we think it would. Instead, it always winds up, one of the most common ones is you stress a system, you try to you put your different boundaries on it to put it under stress, and you try to make it evolve, and it does. But what you wind up doing is you just reprogram the environment in a very, very costly, painful way. So it never comes up with anything new. It just finds a way to mimic what you had. And that's very similar to that. Biology, and this is where I think there's something fascinating about how biology does this. It seems to have an ability to adapt better than we can, at least experimentally. We've not had good luck with this. We almost always try to do it by digital exhaustion of the space. And the one case where I think that really worked out well was AlphaGo. AlphaGo, that's the only case I've ever seen of a system that actually gave me a shiver when I read it. I said, oh my gosh, this system just totally blew the pants off what humans can do. That's the only one I've ever seen that. Now, AlphaFold is a marvelous system, but that doesn't give me that kind of feeling because there's an enormous amount of training. I think the Alpha was just a marketing choice in that. But AlphaGo had a constrained exploration space, and they could do digital evolution by exhaustion and go into that space. But the trouble is that seems to be a very niche area, and it never works well with the physical world because the physical world never is that fully contained. We always have the uncertainty and the edge and where it goes, and we don't seem to know how to deal with that. And biology, when it does this again, and keep in mind, all of this evolution that's going in biology is at that very same level where I just said that Hopfield had some marvelous insights about how is it doing this? How in the heck is it able to take all these random motions and come up with a working molecule? So if I had to to put a wild guess at, it would be nothing more than that, is that biology is using some of those same very unlikely emergence techniques in how it deals with mutations, and we don't know how to do that. So when we get a mutation, it almost always lands into the damaging category. Life, it still is damaging, but life seems to be a little bit smarter, and I think it goes all the way back to that literal quantum molecular, whatever it's doing, ability to say, well, I don't like this, but yeah, okay, here's a path. And life seems to be able to do a better job of finding that path than any algorithm we've come up with. I say digital evolution is a fascinating topic. I used to really enjoy it, and then I just got, after decades, I just got disappointed with it because, like I say, it always wound up being a very expensive way to program, as opposed to genuinely finding a better path.
Thanks. Thank you very much.
Thank you. Anyone else?
Yeah, so I had a question about also about emergence. I think it's understood that you can abandon the concept of intelligence just emerging out of an LLM based on a critical size, or if it ever gets to a critical size. So my question for you is, what other types of technologies beyond LLMs have interest you in finding a better route to human-like intelligence, whether it's some sort of knowledge encryption type of thing, or cause and effect modeling, etc.
Yeah, good question. And by the way, in that part about LLMs not doing that, 3 Stanford professors did it. It's in the references in the paper. I didn't include them in the slides, but they did an excellent study where I think it was Google, one of the LLM groups. I think it was a Google work where they had documented some cases where it looked like they might be getting some few shot emergences, which is kind of code for saying that, yeah, it's figuring out something that they didn't have enough data to really figure out yet. And the Stanford professors, even for those very sparse examples, kind of just really skewered that and said, no, this was a metrics issue. If you use different metrics and come to the exact opposite conclusion for those cases. So experimentally, not having emergence is just, it's hard to deny that it's just the actual data, apart from the theoretical side, is not supporting that. Technologies that might lead to emergence, I think there has to be some quantum and quantum computational aspect to it. And then I've gone different directions on this. And I think the biology, where it mimics quantum mechanics, might be a more conventional way in which they did that. Really interesting presentation, and I hope I'm not, have they published that yet? I'm not sure. I think I'm okay in saying this one, but one thing for neural nets that I think could improve the likelihood of a smarter behavior is the use of complex valued neural nets as opposed to real valued neural nets. I've seen some interesting discussion about that. The reason I think it's okay for me to say that is I've been advocating that for, I think, going on 10 years now. And I just saw a case where some actually did it. And all of a sudden, blurry images that just sort of faded away suddenly got sharp and started doing a good prediction of what the future was. So the reason for complex valued is because everything in real neurons is phased. And the irony is, even back in, I think, 43, when they did the first papers on some of these ideas, they knew that. They knew that there was inhibitory and excitatory phases. But I think, I can't remember his McLaughlin, but the fellow who first came up with it, he didn't want that. He didn't want that complexity. He wanted something simpler. So I found it deeply ironic that they had not gone to that. if you pay attention to phase and how incredibly important phase is in actual neural networks, to me, that just says, you know, complex numbers are a better form for doing that, because it's really replacing one number or two numbers, but conceptually, it just keeps track of that phase. But more importantly, the computations just snap into a whole different domain. And this whole idea of action potential, minimization of action, suddenly becomes an inherent part of that. And that is one of the themes I would say, that if you want more powerful systems, stop using just simple real number statistics and averaging. Start getting into where you do things called minimization of action. Now, if you're not familiar with it, this is action is the quantity that binds those two representations together. So you have the wave representation, you have the point representation. Action is the units that Planck constants are written in, but it also applies to the classical world. So, but seeing these results and seeing some actual examples where they showed that effect, that, you know, a prediction of where an object might move in the future, instead of just becoming a diffuse blob, suddenly it sharpens up and you get a probability that's going to go in this fashion. I think that is some good immediate term directions, is just getting a little more clever on how closely we map actual neurons when we try to build these devices. And the simple, cheapest, that's the one, simplest, cheapest one. Again, I hope I'm not presuming on, I say this on the basis, again, I've been advocating this for 10 years, so it's certainly not a new idea. I've said it in many meetings that folks ought to look at this complex value, but I think there's some interesting potential there. Long-range quantum, as defined by the, what was the name of that recent, there's a recent paper on how the same amino acids that are used structurally are capable of a long-range suppression and enhancement quantum effect in thermal systems. So it's, I don't know how many decades I have complained about Roger Penrose's idea that you're having quantum effects. And I have actually sent him emails, and once or twice got a reply and said, why do you keep focusing these giant molecules? They're not quantum. And the whole story that turned out got a lot more interesting when some real studies found out there's these suppression effects. The phenomenon is related to what makes lasers work, where you get photons can have. So I've overdone that one. But yes, I think some of the quantum aspects, and there's some interesting stuff that has been going on long-term thermal range effects that nobody knows about.
Thanks. Some really interesting concepts in that response. Thank you.
Thank you.
Okay. Yeah, just for the interest of time, we're just gonna have there was just one question in the chat. Mary asked, have biologists offered a critique of LLMs and neural nets?
Bioneurologists are a mix of heavily using these models, elaborating on these models. I think the most common attitude is to make good use of these as tools and find better improvements for them. I'm talking about from a relatively small subset. Biologists in general, I would not know, but for ones who are interested in neurological research and how in the heck our brains do some of the astonishing things they do, which is just becoming more and more apparent, not less apparent as the sensors get better. They're just, they want to use these as tools. They're good starting points, but everybody wants to make them better and to feed in some of this remarkable data that's coming in from modern sensors. I'll give you one quick example. A modern sensor, something called a 2-photon sensor, allows you to actually poke at a single neuron and find out what that neuron is going. Did you know that there are lasers that can now adapt to your retina and see every single cell and activate them individually And I've talked to people who have seen a color that cannot be mapped onto any existing color chart because the color does not exist in nature. Now, the color itself is a blue-green color that is not, it's not a totally different color from that, but there's an intensity to it, and there's some parameters to it that are not possible with normal human vision. So in that sense, these folks can actually see a different color. That's the level of tech we're getting these days. We're getting just some of the things that is possible to measure now was inconceivable not that many years ago. People who can query the entire 6 levels of the neuron simultaneously with various optical and mechanical techniques. New sensors, there's a lot going on, and it's looking at the LLM stuff. They're not worried about the language model stuff. They're worried about the real use of it and saying, how can I use this to make better models? So I think it's a good synergy going on right now.
Okay, awesome. Yes, so we are at the 3 o'clock mark. So I think we are just going to wrap it up here. I did notice a hand that was up before, but it's not up anymore, so I guess we're good on that. Unless just want to hop in really quick or okay. Okay, cool. Yeah, no, Terry, just want to say thank you for the chat. It was actually a really interesting topic. And I think it was like pretty helpful for people, with like little experience to like a high knowledge in the space. So I thought it was an interesting discussion and a presentation overall. Thank you so much.
Thank you. Much
Yeah. And in terms of everybody else, thank you for joining today to another meetup on a Saturday on Halloween weekend. But just wanted to give everyone a heads up that the next one will be November 16th at 1 o'clock Eastern Standard Time. Remember to push your clocks back an hour today because daylight saving time is officially over starting tomorrow. So 1 o'clock Eastern Time, November 16th. The topic will be a series challenge to quantum mechanics, part 3, a theory, led by Dr. Paolo Gora. Yeah, that's it on my end. Terry, was there anything you wanted to say on your end?
I just appreciate the chance to talk. Thoroughly enjoyed it. Thanks. Great questions. Appreciate the questions.
Thank you very much. Yeah.
Great. Helen, was there anything on your side as well?
Yeah, you have more discussions, please go ahead to discuss. I see Jordan just raised his hand.
Oh, okay. I guess Helen will stick around for the last minute. Terry, I guess, are you free to stick around as well?
Yes.
Okay. All right. So I guess, yeah, if anyone had any other questions.
Thank you. Terry, I want to say thanks. And what I wanted to just add to this was, with the inherent risks of a probabilistic nature of a stochastic system, there's also increased risk with data integrity. So the whole area of this new attack surface of poisoning the training data, prompt injections, also increases risk with the system on top of the, how you proposed of having this type of system, the risks multiply, so to say. And I just want to say thank you, too. I really enjoyed the presentation.
Well, thank you. And I would agree with your point emphatically. The insidious, I use the word insidious because that's the slow burning one. I think the corruption and the intentional corruption and subversion is an enormously higher risk right now because that is hard to handle in these systems. So good point. Thank you.
Do anyone have more questions for Terry? Seems like there's no more questions.
I think looks like we're good.
Yes. So if you have more questions, we can reach out back to Terry. Thank you for coming. Goodbye.
Okay. Thank you, everybody.